All right, folks, this is the last idea in Chapter 7. What we're doing is, in the previous section, we said, well, there's an equilibrium constant, and we can do calculations associated with that. Here the idea is we've allowed a system to come to equilibrium. We put in reactants and or products, let it sit until it's reached that point where the concentration of reactants, concentration of products is no longer changing. This is what's in a biological system, right? You've got some system and it's sitting there at equilibrium. Now, there's some disturbance, and what we want to say is, well, what happens, what we want to look at is what happens when we disturb that equilibrium. We could do this with a lot of math, but it isn't really necessary or appropriate for Chem 51, so we're going to just sort of look at it more qualitatively. Well, this is commonly called LeChatelier's principle, that if something's at equilibrium, it will respond in a certain way. So I'm going to imagine some sort of reaction vessel here. Something like this. Here's my reaction vessel. And I have some kind of lid on this thing that I can push down or pull up. And I have some valve on the side of this thing, so I can put reactants or products in or out. And I'm going to say, well, here it is sitting here at equilibrium. There are, 5 million A atoms. And there are, let's say, 4 million Z atoms. And there's a little bit of product. AZ2, let's say there are 2 million AZ2. There it is. Now I know these are reacting. A's are reacting with Z's to make AZ2, and AZ2s are falling apart, but we don't see any difference. So what I've got here is my initial conditions are at equilibrium. Again, I put in products and or reactants, let it sit there, and it's reached equilibrium. So the idea is we can disturb this somehow. I could add or remove reactants. I could open that valve, inject more reactants. There's a way I could remove specific reactants, so I could change the amount of reactants in there. I could do the same with products. I could inject some product, or I could remove some product. I could change the temperature. Now, the way I'm going to say that is I can add or remove heat. And lastly, I could squeeze this thing down. I could expand this thing by moving this lid up and down on this thing. That gives me a change in volume. And what we really are looking at really then is, if I change the volume, if I squeeze it, what do you think happens to the pressure? If I expand that lid, what do you think happens to the pressure? Well, let's think about this. So here's some common changes. Get some reactants, take some reactants out. Take some products out, add products in, heat the system up, squish the system. Well, what I'm really getting here is a change in reactant concentration. If I add reactants or room rank, well, I'm changing their reaction, their reactant concentration. Products, same thing. I could say, well, I can change the concentration of products in my equilibrium mixture. And remember, these are what we use to calculate K. That says this is equilibrium. These are the equilibrium quantities, and now I'm going in and changing them. If I add or remove heat, I'm really changing the temperature. And we sort of did this mental experiment that if you change the volume, you're changing the pressure. So I have all of these changes. LeCHATELIER is like one of those little kids with oppositional defiance disorder. Whatever you do, the kid tries to undo. You know, you stack up the toys, the kid unstacks the toys. You write on a piece of paper, the kid erases the paper. That's what LeCHATELIER is doing. LeCHATELIER, we say, you know what? This was at equilibrium. Then you messed with it that produced a change. LeCHATELIER said the equilibrium will, quote unquote, shift to undo those changes. So responds by, we'll say shifting, we'll see what that means in a minute, shifting equilibrium to undo all those changes. That's the big idea. Now, shifting equilibrium, LeCHATELIER has two choices. LeCHATELIER says, you know what? I can make the forward reaction go if that will undo those changes. If I have to, I can make the reverse reaction happen to undo those changes. And that's it. That's the whole idea. Oh, okay. He wants to undo this. Which way does he have to shift to return it back to the equilibrium condition? I'm going to do a sort of complicated problem, and then we'll come back and take it apart very slowly, piece by piece. So I'm looking at page 7.28. Here's my reaction. And I'm going to think of it as like this is inside some kind of vessel. Now the first thing we're going to sort out here is it exothermic or endothermic? You might stop the video and, oh yeah, what does that mean? Positive delta H, endothermic. Now we can do something kind of weird. Remember, endothermic means heat is added in to make the reaction happen. Heat is pulled from the surroundings to make this reaction happen. Heat is a reactant. So I could say, you know what, I'm going to write this 285 kilojoules right there. It's endothermic. It takes 285 kilojoules for every 3 moles of O2 to be converted to 2 moles of O2. Since the reactants or products favored at equilibrium, well, that's a pretty small number. Not much of this product is made. Now here are my disturbances. I'm going to decrease the volume and increase the overall pressure. Another experiment, I'm going to increase the concentration of O2, increase the concentration of O3, add a catalyst, or increase the temperature. There are my 5 different disturbances that I'm going to impose on this thing. So the first one says you're going to increase the pressure. LeCHATELIER says I want to decrease the pressure. There's our LeCHATELIER response. It was the equilibrium at whatever the pressure was. You squeeze the container, the pressure goes up. LeCHATELIER says, I want to return the pressure to what it was under equilibrium. Now this is a little bit tricky. This reaction is 3 moles of gas on the reactant side, 2 moles of gas on the product side. So think about this. It's very much just sort of intuitive. 3 moles of gas here bouncing around, 2 moles of gas there bouncing around. How can I reduce the pressure? Fewer moles of gas. There's LeChatelier's response. He says, I'm going to take some of those 3 moles out, convert them into 2 moles. That'll give me a lower pressure. So I might even make, well, let's leave it at that. That one's a little bit subtle, but if you just know that fewer moles of gas is lower pressure, more moles of gas is higher pressure. If I want to reduce pressure, he's going to shift, he's going to run the forward reaction more to reduce that pressure. Now, there are always collateral effects if the forward reaction runs, some of that O2 gets used up. The concentration of the O2 will drop. If the forward reaction runs, some of the O3 is produced and the concentration of O3 will go up. Let's look at the next one. The disturbance is increasing the concentration of O2. So increase concentration of O2. The LeCHATELIER response to bring it back to equilibrium is to decrease the concentration of O2. So we could say, well, he really wants to do that. He wants to undo it. Now, does he run the forward reaction to reduce the O2 concentration, or does he run the reverse? Well, he wants to run that reaction. Use up this additional O2. Well, the collateral effect, the O2 gets reduced and the O3 concentration increases. So this is the key thing. What happened? What's the disturbance? What's the response? Does he go right or does he go left to respond to undo that? 3 says we're going to increase the concentration of O3. LeChatelier's response is to decrease the concentration of O3. So I can say, okay, we increase the concentration of O3. LeChatelier says decrease it. Well, how could he use up the O3? Could run the reverse reaction. Now the collateral effect, oh, I should have done that in red. Plus, minus. Now we can do all this mathematically, but really the most interesting thing is just to see when I disturb an equilibrium, what's the response? What can I expect more of? What can I expect less of? Now the disturbance in 4 says we're using a catalyst. Used, past tense, present tense. We're going to use a catalyst. Now what does a catalyst do? Well, it makes the reactions go faster, right? What does it do to the forward reaction? Speeds it up. What does it do to the reverse reaction? Speeds it up. I can say, well, both are faster. Well, it doesn't mean there's more of anything. It just means it gets there faster. I still have my reactions occurring. They're just going back and forth faster. There's no effect. Catalyst just makes those reactions that we know are both happening at equilibrium happen faster, and we see nothing. It's like you're walking backwards on that people mover conveyor belt. They speed up the conveyor belt and you speed up. It doesn't change your position. The last one says we're increasing temperature. So let's say increasing temperature. Well, really, we could say, well, we're adding heat. Well, LeChatelier said, reduce the temperature, remove heat. Well, there's my heat term. Since this was endothermic, I put the 285 kilojoules right there. So I can say, oh, well, if I want to remove the heat, that was sort of added, I want to remove the heat. Now I can think about the heat as a reactant, like any other reactant. If I want to remove it, I'm going to run the forward reaction to quote-unquote use up the heat. Well, I'm going to decrease the concentrate. I should have used red again. Dang it. I'm going to decrease the concentration of O3, and I'm going to increase the concentration of O2. Now, let's do this again and break it down even to a finer detail. Well, let's do this example. Page 7.29. Here's my reaction happening inside a vessel. There's my little box. I'm saying that's going on inside there. Now it says, LeCHATELIER, write the reaction equation with heat as a reactant or product. Oh, I should have maybe taken that out of there. Yeah, I got a better pen. Watch this technology. Here's my reaction vessel. Nice. Endothermic. So that means I have to add it in. What is this? Kilocalories on the reactant side. It says note phases. There's gas, gas, gas. So I've got 3 moles of gas going to 2 moles of gas. And then let's make a little table out of this. Make a little table. Let's go stress, response, and then we'll do this. SO3 concentration effect. I should have made more room there, huh? Okay. Is SO3 favored by higher or lower pressure? Well, if I want to make this go up, I want the forward reaction to happen. Well, I'm going 3 moles of gas to 2 moles of gas. How do I force it to go to the 2 mole side? Low pressure. If I lower the pressure, LeCHATELIER will constantly be trying to bring the pressure up. Sorry. High pressure. If I subject this equilibrium to high pressure, he'll constantly be trying to lower the pressure. So LeCHATELIER will constantly be trying to take these 3 moles of gas and reduce them down to 2 moles of gas. Same thing, I want more of SO3. Well, what would force it to go to the right? Well, if I add heat, it's going to try to use up the heat. So I'm going to run this at a high temperature. If you've got it at equilibrium, you increase the temperature, this endothermic reaction will try to use up that heat, and it'll constantly be shifting to the right. So high pressure, high temperature. It's another way to think about it. In industry, we're often thinking about, well, I'm going to put a plus there. I'm trying to get more product. Well, do we run it at a low temperature, high pressure? Low temperature, high temperature. Low pressure or high pressure. And I don't know anything about biology, but biology is based on this. It's trying to get some reaction to happen, some product to happen, and it's constantly doing this sort of what conditions are changing to produce more or less product. All right. Let's look at page 7.30. We'll break this whole thing out. Okay. Let's go step by step and break this down further. About half of the class probably right now understands this. Like, oh yeah, I get this LeCHATELIER thing, I can do this. About half of the class is still sort of not quite there yet. So that's what this is for. If you get it, you might turn off the video and go to the homework. But if you're still sort of struggling with this, these last 2 pages are for you. Okay, here's my reaction I'm looking at. I've got to get two gases, one gas, 1 mole of gas. It's exothermic. I'm going to write the 75 kilojoules out there. Now here's my sealed container. I'm going to put plus 75 kilojoules because that was negative, right? So, okay. So now there's my equation where I've written heat as a product or a reactant, exothermic. It's a product. So the question brings us back to, have all the reactions stopped at equilibrium? No. There are still forward reaction and reverse reactions are still happening. So what I want to do is think about, okay, what happens when we run the forward reaction? What happens when we run the reverse reaction? We're not talking about disturbing equilibrium. We're just taking a step back and saying, well, what happens when I run those two different reactions? So here I'm showing, let's just pretend I'm only looking at the forward reaction. Well, if that reaction happens, H2 concentration decreases, right? CH4 increases. The total pressure, 2 moles of gas dropping down to 1 mole of gas, the total pressure decreases. The temperature of the surroundings, well, if I run the forward reaction, I'm producing heat, giving off heat. The surroundings get warmer. So all I've done is just taken a step back and say, well, wait, what happens when we, or LeCHATELIER, runs the forward reaction? There are the effects. Well, conversely, what about if I think about only running the reverse reaction? Oh, the concentration of H2 would increase if LeCHATELIER ran the reverse reaction. The concentration of CH4 would decrease if LeCHATELIER chose to run the reverse reaction. The total pressure, going from 1 mole of gas to 2 moles of gas, would increase. The temperature of the surroundings would drop. If I go to the left, I'm using up that heat. I'm pulling heat out of the surroundings. So these are LeChatelier's two options. Run the forward reaction, you get these effects. Run the reverse reaction, you get these effects. So all we did, we're not shifting any equilibrium. We're just saying, what if we shifted the equilibrium? What if we decided to run one reaction instead of the other? What's the effect? Now I hope that helps. We think, oh yeah, there's two reactions. LeChatelier could do this, or LeChatelier could do that. Now with this in mind, let's look at the last page. There's our reaction, just that we just looked at. Now I'm going to say the disturbance is add heat. LeChatelier's response, remove heat. Well, there's my heat term. That's what LeChatelier wants to do. Now on the previous page we said, oh, if you want to remove heat, you run the reaction, the reverse reaction. My effects, increased hydrogen, decrease concentration of methane, CH4. Now you notice I'm not doing anything with this solid column. It's a solid. It has no impact on the equilibrium. The next disturbance was increase pressure. LeChatelier would say decrease pressure, bring it back to the equilibrium conditions? Well, 2 moles of gas on the left, 1 mole of gas on the right. The only way you can decrease pressure is go to fewer moles of gas. So the effect, concentration of H2 decreases, concentration of CH4 increases. The last one here is pretty explicit here. It says the disturbances increase the amount of CH4. And really, in a sealed vessel, if I put more in, I've increased the concentration. LeCHATELIER would say, I apologize to anybody who's from France, my bad accent, decrease. So if I come back here, it says, oh, you increased concentration of CH4. LeCHATELIER says, I want to decrease it. Does he go forward or back? He goes back. Effect like that. Now we can do all this mathematically, but I think this qualitative approach is even better to sort of think about, well, if you change the conditions, what's going to happen? That's LeCHATELIER. From equilibrium, we disturb it, and LeCHATELIER says the forward reaction or the reverse reaction will run to try to undo the disturbance. The next 2 pages, the last 2 pages in this chapter, are just a summary, bring it all back together. Chapter 7 is huge. We would spend a month and a half, maybe 2 months, in a Chem Majors course. I love this stuff, of course, but it's really a fundamental idea, some big ideas and lots of ideas in here. So the last 2 pages we'll review, but this pretty much wraps up Chapter 7. If it all makes sense to you, it's time to dive into the homework. If not, or even if it does make sense, the next 2 pages, the last video for Chapter 7 will be that summary. All right, I hope everybody's well, and I'll see you at the next video.